Okay, it's my privilege to introduce Pravesh Kothari. He was my PhD student. I forget what year you graduated, but
2016.
2016. And for several years was a professor at CMU and then has very recently moved to Princeton. Is super famous for his work in both, computational complexity, coding theory, and learning theory and robust statistics. He's won every award, including like the Pressburger Award last year. So,
recording in progress.
Great to have you here, and I'm sure it always gives amazing talks. So, take it away. I'm happy you're here.
Okay, thank you all for coming, and thank you for the great introduction, Adam. It's kind of hard to live up to it, but I'll try. So I want to talk about a couple of papers on this topic called Semirandom planted Clique. If you have seen the planted Clique problem, this is some variant of it that I will talk about, algorithms for. But if you haven't, no problems, I'll tell you a little bit about the story for why you might care about it, okay? I should apologize. I have an old version of this talk where I have a more complicated algorithm, but I want to describe a simple algorithm to you. But I didn't manage to make slides for that version. So I'll stop midway and I'll move to the board and I promise to give you the complete proof. Okay, so that's the plan.
So, right, this is the same plan. When the CST is speaking here. So Laurent Massoli and all these people talk about planted Clique. Is it the same planted Clique problem or is it a different one?
Good question. So the people you're talking about, they usually think about the much sparser version of this problem because they're looking at this community detection or stochastic block model. And then they are really interested in like the right constants, like, they're looking at like this Keston's eigenthreshold. We are going to be in a version where we wouldn't have to care much about the constant because I'm going to look at dense graph version of these problems. So yeah, same problem, but like different regime. Yeah. Okay, perfect. Yeah, so this is joint work with Rajesh Buhai, who is an amazing PhD student. He's actually graduating this year. If any of you have an opportunity to hire him in any form, please do. Jarek Blasiuk, who is a postdoc at ETH, and Stoirer, my longtime collaborator. Okay, great. So let me start by just talking about the Clique problem, which all of you might have seen before. Given a graph, tell me, find me a vertex set so that all the edges between them are present, right? Like find me as large a set as possible. And if you know this problem, you also know that this is kind of, very well studied and is super duper hard. Let me just remind you how hard. So, given a graph, the best algorithm we have can do the following. Even if you give me a graph which has near linear size Clique, meaning like n over polylog n vertices are contained in the Clique, the best thing we can do is find about log square size Clique. I wouldn't focus too much on the numbers here. I just want to give you a sense of the problem being super duper hard, right? Like the hopelessness is the point. So yeah, and then we know in some sense that this algorithm that appears over there is more or less basically the best we can do in the sense that we have a near linear factor hardness. And so in some sense, if you think from the perspective of algorithm design, not much for us to do, right? Like you could try to improve the log square n to polylog n, etc., but it kind of seems hopeless beyond that point, okay? That's great. So what should you do? Well, already in the 70s, after proving the NP hardness of 22 other problems, Karp was thinking about this question. He said in 1976 already, he was thinking, well, this problem is going to be super duper hard. He didn't know of hardness of approximation at the time, but he was already wondering what should we do. And he said, maybe we should be making more assumptions on the inputs, right? Like that's the way to inspire new algorithmic ideas. So he started considering this average case variance. And the version I'm going to talk about is really a variant that came out of hopelessness of even the average case variant that Karp proposed, okay? So Karp basically asked the question of like, find me a largest Clique in Gn1/2. The largest Clique is of size about 2 log n. There's a greedy algorithm that does 1 times log n. And in 76 he asked, and in 2025 we cannot do anything about, is beating the greedy algorithm that does 1 times log n. Like find me a 1.1 log n times Clique, we don't know what to do, okay? Anyway, so the planted Clique problem is a relaxation in some sense of even this problem that was introduced in these works of Jerem and Kucera. They said, suppose I give you a graph where I start from Gn1/2, then I take some k vertices and complete the Clique on them. This is like a planted Clique. And this time k would be larger than 2 log n. So it's definitely larger than the maximum Clique, with very high probability in Gn1/2. So it is with very high probability the unique max Clique in this graph. Can you find it? Can you find this planted k Clique? That's the problem. Okay. So just because the largest, yeah, sorry.
Does the planted Clique
Is it also depend on the randomness of the sampled edges?
Yeah, good question. For the results I'm going to talk about, it doesn't matter, right? But it's a good question. In principle, the two problems have a slightly different formal notion of difficulty, but all algorithms work for either variant. Good. Okay, so just because GN1/2's largest clique is 2 log n, you can just look for like 3 log n size cliques, and you can just like piece by piece reconstruct this size k clique in n to the log n time, or n to the order of log n time. So quasi-polynomial is obvious. And the question is, can you get polynomial, right? Like that's the kind of gap we are playing with here. And so, back in the 90s, when people were super duper excited about inventing the first spectral methods, there was this very cool paper of Alon, Krivovich, and Sidakov. They observed that by looking at the second eigenvector of the adjacency matrix of the graph so given, you can basically extract a clique if k is at least square root of n. Okay, and this is based on very simple fact that if I take a GN1/2 without clique graph, look at the plus minus 1 adjacency matrix, or equivalently look at the 0, 1 matrix, but look at the second eigenvalue, then it's going to look like 2 times square root of n. Now, this is a basic random matrix theory fact, and you can show that by adding a k clique, you bump up the eigenvalue to about k. So if k is bigger than 2 root n, then in some sense, the eigenvector will be governed by this planted clique, the indicator of the planted clique as the planted eigenvector. Okay, so that's very simple idea. Back in the day, like now it's trivial, like you could do it in 10 minutes, but in the 90s this was the very first or like maybe second or so application of spectral methods, so it was very hit. It was a cool result. And then people observed that you can actually beat it. You can actually handle any constant times root n instead of like a fixed constant times root n by just allowing more running time. So more precisely, you can get an n to the t time algorithm if the planted clique is like k, which is root of n over 2 to the t. So really, like there is no asymptotic improvement if t is a constant, which is all that you're allowed in polynomial time. But you can make it like you can find cliques of size epsilon root n for any fixed epsilon. That's all good? Okay, great. And there are some. So in average case world, we are kind of very bad at proving lower bounds. We haven't managed to give reductions that relate these problems to worst case hard problems that we believe are in some sense hard with more certainty. But we have restricted lower bounds that suggest that beating these kind of guarantees would be hard. Okay, but we've got no great evidence, only limited evidence like that. Okay, good. So that's the story of the average case variant. This seems nice in the sense that there's a little more room for algorithms, right? Like we're able to get non-trivial algorithms. If you think of it as an approximation algorithm, you are approximating the clique by root n factor in some sense. Even though linear things was basically disallowed in the worst case, so you're doing a bit better. Algorithm-wise, you also seem to be doing a little bit better in the sense that you're able to use spectral methods and SDP. So it seems like okay, there is some scope for cleverness. Okay, except there is a problem. Or I guess I would argue there is a problem in the following sense. The algorithms that we design in this context, they turn out to be brittle in the sense that they fail catastrophically, even if I were to make a very small, arguably minor perturbation to the input. Okay? So just to give you an example, think about the following simple algorithm that already solves the planted clique problem if k is square root of n log n instead of square root of n. It's a bit worse, but it's a simple algorithm. This algorithm simply observes that the degrees of GN1/2 vertices are concentrated around n over 2 plus minus square root of n. If you add a clique of size square root of n log n, the maximum degree vertices will be the ones in the clique with high probability. You can just take them and go home. Okay? This is an algorithm. It solves the problem essentially optimally up to like root log n factor. On the other hand, it's a weird algorithm because I can modify the degrees of the graph very easily by just touching like sublinear fraction of edges, right? Like sublinear number of edges. It's very easy to defeat. Order of n log n edges would be enough if I touch, to completely beat it. Now, this is not just the problem with degree algorithm. It's actually also true about the spectral algorithm. The eigenvalues are famously brittle parameters. You can, modify the graph in like sublinear, sub-constant fraction of edges and really make the eigenvalues tell you nothing about the planted clique. So the problem I'm trying to mention is that these algorithms in some sense that we are discovering, we could be happy about them, but they're also in some sense overfitting to the assumption that we made. They're overexploiting this fact that degrees are very tightly concentrated around n over 2, or the spectral norm is very tightly concentrated around 2 root n, etc., etc. Facts that maybe we are not super happy so strongly tied down to. Okay, good. So that motivates the question of whether there are algorithms that somehow don't do this.
When you say you'd be deleting edges outside the planted clique, you mean edges with one vertex in the clique?
So you know, I could create larger degree vertices by only touching the edges that don't even touch the clique.
But by deleting those vertices, you're only going to make the degrees of the vertices.
Oh, right. Yeah. If I have to, yeah. So, yeah.
Right, I got
Yes.
it.
Absolutely. Right. If it's modification, then you know I don't even have to touch the clique. If deletion, yeah, then I can, yeah.
Got it.
Good. Perfect. Yeah. Okay. So that's the question. Like, you know, are there more robust algorithms? How might we motivate them? How might we find them? So, you know, this is not maybe a specific to Clique kind of a theme. There are like lots of different investigations within algorithm design that all focus on problems of the same philosophy, same philosophical reason. So if you know robust statistics, it's motivated from similar considerations for estimation problems. If you know smooth analysis, that's kind of similar motivation, but for like, you know, trying to design algorithms that, you know, handle perturbed inputs or something. And today I'm going to talk about this third way to think about beyond worst case analysis, the semi-random models. Okay, so let me tell you a little bit about, you know, what we know about these models. So they were introduced in this very cool paper in the context of graph coloring by Blum and Spencer in the 1990s. This paper and like works around them, in fact, are the works where all these, you know, big progress on coloring three colorable graphs began. So, you know, like later on, Blum followed up this paper, and that was like the starting point of this line of work. But Feige and Killian took this Blum-Spencer paper and like took in a different direction. They observed that there's nothing special about coloring. We should really be thinking about semi-random models for a lot more problems, Clique, CSPs, whatnot. And, you know, by now, this project that they began has been really done to death for like lots of problems. KSAT, coloring, Clique, community detection, you know, what Sanjay was mentioning earlier. So lots more, you know, work in this direction has now already happened. It's obviously more challenging to design algorithms for this model, but on the other hand, you have some more confidence guarantee that these algorithms would be more relevant or more useful, okay? So if you want to learn more about it, I recommend this, you know, book. There's like 1 out of 5 parts of this book devoted to semi-random models for various problems, what we know about them. And yeah, so it's a bit dated in the sense that a lot has happened in the last 5 years, and this book is from 2018 or 19, but still, I think a lot of classical work is covered in this book. Good, okay, so let me tell you the model that I will care about today. Okay, so this is the model that Feige and Killian introduced in 1998. You can think of this model as selecting the graph in, 2 or 3 phases. Very roughly speaking, the first phase is like you start from the vanilla planet Clique problem. And then in the second and third phases, an adversary comes in and gets to modify the input by looking at the graph sample in a way, so there's going to be some restriction, but they're going to try to make your life hard. And the idea is that this combination of worst case and average case choices will on the one hand allow you to steer clear of worst case hardness, but on the other hand prevent you from overfitting to some quirky properties of the random model. Now of course this is to be argued upon whether it works, but that's the idea. Okay, good. So the first step is just select a graph from the planet Clique model, the one that I talked about earlier. The second step I'm going to call the adaptive modification step. What you're going to do is modify the edges that do not touch the vertices in the planet Clique arbitrarily. You can add edges, you can delete edges. So effectively speaking, you can make this blue part of the graph completely arbitrary, okay, and you're allowed to do that. Okay, does it make sense? This I'm going to call the adaptive modification step. I'm also going to allow the monotone deletion adversary, which means that the adversary comes, looks at the graph, and then can delete an arbitrary subset of edges that go between the planet Clique and the rest of the vertices. So what's the restriction? The only thing the adversary cannot do if I allow all 3 things is they cannot add edges to this cut. If I gave them that freedom, then this is the worst case Clique problem. Okay, does it make sense? Good. Okay, so equivalently you can think of this model as like first planet Clique on S star, choose edges that go out of S star at random, so G and 1/2 distribution, every edge 1/2 probability, right? Then you just choose an arbitrary graph here, and you can delete any subset of edges here. That's an equivalent description of the model. This is me just filibustering so that you have time to digest the model. Okay, great. So, yeah.
But wait a minute, I mean, in particular, you could add a clique to V minus S stars that was slightly smaller.
Excellent.
Okay, but then, how big of a clique do we need to find?
Excellent. All of these are great questions, and I'm going to answer Scott in one slide. Okay?
All right.
So, but before that question, I want to talk about, I want to filibuster a little bit more. Okay? So, if I delete all the second and third step, it's the old problem. We know how to solve it. Okay? So you already, starting at some non-trivial step, okay? If you delete this second step, actually it already turns out to be a well-studied model. This, 5-year Killian paper introduced a bunch of different models for, semi-random versions of the problems. And some of them were, solved early, some of them remained open for a while. This one was solved early. So Feige and Krautgammer said that if you only have deletion adversary, if you don't, touch this part of the graph, it remains random, and here you delete any edges, then, it's called a helpful monotone adversary. It's helpful because in principle, it's only making this clique more prominent, right? Like less edges are going outside of it. In principle, it should only help you, okay? Well, it's not so clear it really does help you because the spectral algorithms will break even with this change. The degree algorithms, you can make them fail even with this change, okay? Nevertheless, Feige and Krautgammer, about a couple of years after this model came out, showed that SDP works. If you analyze the so-called lower theta SDP relaxation, that works at the same threshold as the best results for planet Clique, but it also handles monotone deletions, okay? So now, we are looking at this semi-random model, and as Scott observed, the blue part can do anything. So Scott was worried about, smaller cliques, but I can add a huger clique there. I can make the whole thing a clique. I can make have n over k different cliques of the same size appear there. So what even is the question? I can't quite hope to identify S star uniquely anymore, right? Like this is the conclusion. Like, there is no defining property of S star that I can try to preserve in a unique way, right? So yes.
In this model, is there a S star size log n, or right now you have specific?
Oh yeah, so it's going to be, we are going to a harder problem. So k will always be at least root n.
Oh, okay.
Okay, because my benchmark is the fully random planet Clique model. I'm not trying to beat the results there. That would be breakthroughs and it would be great. I'm trying to make incremental stuff happen. I want to do this model and match the results of the fully random planet Clique. Okay, does this make sense? Okay, good.
And then when you do adaptive modification, is there a cardinality constraint on how many edges?
No.
No, arbitrary.
No, yeah. So that's why the adversary can make an arbitrary graph here, right, if they want. Okay, so what's even the goal? Well, I'm going to do what coding theorists will do. Instead of uniquely decoding S star, which is impossible in this regime, I'm going to list decode or try to list decode. I can't give you S star uniquely, but give me a small list that is guaranteed to contain S star, and I'll say okay, you won. Okay, that's my goal. Yes?
What if you find just one clique of size 8?
Yes,
Is
excellent.
that just as hard or easier?
Great. So the question that Shuchi asked is exactly what Feige and Killian asked. That's what they said the goal is, find any k clique. I don't care about maximum clique, find a k clique. Okay, that's great. It turns out that all known algorithms really solve this last task. It turns out that's the only way we have to solve any of these 3 tasks. And the last task is, of course, it subsumes the other 2. So in principle, finding a k clique could be easier, but we don't know how to do that, any better than just finding a list of k cliques that contains it. Yes?
I think you just said, so you want this clique to be contained in
Yes.
one of them?
Yes. Yeah, I want to find a good list. Yeah. So this is in some sense, I'm trying to make it an estimation problem, right? Like this first thing is an optimization problem. I don't care about finding a star. I'm not trying to recover a planet signal, right? The third thing makes it like a signal recovery problem. Right? Like there is a certain signal about S star and I want to recover it. Yes.
3 only implies 2 if you promise me the list contains the one with S star.
Yeah, that's a typo.
Oh, okay.
Yeah, find a list of size n over k cliques that is guaranteed to contain S star. I understand the confusion. Yes.
I got confused once you asked your question.
Yes.
There's basically partition a constant fraction of the graph into k cliques.
Yes. It may not be possible, as in maybe the graph doesn't have a partition like that.
Right.
But
Partition as much of it as you can. Or
Exactly.
As can be. partitioned.
Exactly. That's the
So
goal.
you're saying it's better if the list is big?
No.
Okay, so it's okay if it's not a partition.
Yeah, so okay, so I understand the confusion again. So here's a bit different way to think about it that might solve both the questions. You can imagine that the best damage the adversary can do to you when they are trying to make it harder for you to identify S star is they could just try to replicate this model about n over k times. Say S star and edges going random. There's no way to tell which was S star. If you try to do this, you'll be n over k cliques, right? We are saying, the unsought, so assumption is that this is somehow the worst case, match the guarantees you could do for this case. We don't know it's the worst case, but that's the intuition. Does that make sense? So larger list is not better, but like n over k in some sense is the right size. Yes?
I mean, also, I think, just finding a k clique is already a motivated problem.
Yes.
And this is a strictly harder thing.
Yes. Yes. No, he is worried from the list decoding perspective, and of course, if I give you a larger list, it's a bit confusing. But anyway, yeah, I think we're all on the same page now. Good, excellent. That's the problem we'll focus on. Okay, and there is nothing new in there. Like all algorithmic results for this problem really did this task number 3 anyway. Okay, good. So, let me tell you a little bit about what is known about this problem. So, the basic SDP doesn't work. Okay, and this was observed back in 2001 that any fixed algorithm like that is easy to break. And the reason is simple. This part could simply encode the integrality gap instance for Clique. Right? And the SDP would basically entirely focus there. And so now, you have no information about S star. And so there is no reason why you'd be doing anything better, right? So that was observed a long time ago. And so the best known algorithms are based on like some variants of these SDPs that force some additional entropy-like constraints. Like you want your SDP solution to be spread out. You want to say like, somehow don't give me a solution that focuses only on a part of the graph, but it's tricky because maybe that's the only clique, right? Like maybe you can't expect this to happen. So there is a way to enforce as spread out as possible kind of a constraint on SDP. We have some entropy-like objectives, and all these algorithms really rely on these kind of entropy constrained SDPs. Okay, that's how they work. And the first recent improvement to algorithms for this problem happened in this work of Cheriker, Steinhardt, and Valiant. And they showed that there is a polynomial time algorithm. They were looking at the model without deletions, which is, by the way, the one I'll focus on today. So, without any monotone deletions here. In this model, they showed that if k is at least n to the 2/3 up to some log factors, you can actually recover the S star, or you can recover a list which contains S star, okay? And then, there was a very nice paper of Steinhardt that argued somewhat surprisingly that for this problem, there's something really non-trivial that's changing. In the context of, this fully random clique problem, information theoretically, the clique was uniquely identifiable as soon as the size was at least 2 log n. If you ask a similar question here, when is it possible to identify a list of n over k cliques? What's the smallest k for which it works? The answer turns out to be root n, not log n or not 2 log n. Okay, so Steinhardt thought of this as like some kind of evidence that even the information theoretic threshold for this problem has shifted. In some sense, it has been brought down to the computational threshold or guessed computational threshold for the fully random clique. Okay, does this comment make sense?
Sorry, what do you mean by information theoretic threshold? I mean, if I had exponential time, then I could just find a list of, partitioned into these cliques if that existed.
Excellent. So when I say information theoretic threshold, it has to be an estimation problem. There has to be some planted signal I'm trying to recover. Yeah. So then the goal isn't to partition. The goal is to find me a small list. You can't give me an n to the k list, that's trivial, you're right. That contains S star provably. Okay, so this threshold is for list size n over k, so it's very restricted. Right, but it's saying that you can't hope to find me a list of size n over k that is guaranteed to contain S star. That's the estimation problem. Huh? I think it will work with like maybe polylog n times n over k, but it won't work for n square over k square, for example.
But that's good enough.
Yeah. So that's why I say it's only an indication. Yeah. Good. And then, there was this very nice work of Mackenzie, Mehta, and Trevisan that showed how to both remove this log factor and also handle monotone deletions. Again, all of these results, they work by cleverly correcting, this SDP with entropy constraints and analyzing it. Okay, good. So that's basically the summary. Information theoretically, it seems, at least for this super stringent goal of finding n over k size list, there is some root n kind of a thing that's needed. And, the basic SDP seems to get stuck at n to the 2/3. I'm calling it barrier, but I'm not going to justify it in this talk. There's a version of the talk where I justify it. You can prove a lower bound for a related problem here. But today I'm not going to, because I'm going to tell you like a very simple algorithm. So just take my word for it that there is, in a certain precise sense, there's a barrier for the basic SDP in going beyond n to the 2/3 here. Okay? And in fact, this barrier motivated this explicit open question. So Feige phrased it in his book. Like he wrote a chapter in this book, and he basically says, is it really true that the problem is getting harder beyond fully random clique, or is it that we're just missing the right algorithm? And then, Steinhardt posed it for like this model without deletions, and phi really was maybe a little bit agnostic. But basically, in both the models, we did not know, and it's a natural question to ask whether something interesting is going around into the 2/3 or whether we can improve these algorithms. Okay, good. So now I'll tell you the result. So we had this result about a couple of years ago. We showed that in fact, the problem seems to be almost as easy as the fully random clique. It's not that hard. And in particular, we showed that for any epsilon, there's an n to the 1 over epsilon time algorithm that can succeed when k is at least n to the 1/2 plus epsilon. So as epsilon goes to 0, you approach root n, but of course, for any fixed epsilon, you are polynomial away from root n. Okay, does the result make sense? Good. So let me tell you a little bit about this result because I'm not going to tell you too much about this result.
What was the list size? I never got.
Yeah. So yeah, all the results I state, will get order of n over k list size. In fact, you can make it, exactly n over k2. That's not the hard part. Like once you get a small list, you can do some pruning and you can always ensure that the list is no bigger than n over k. So that isn't a parameter to focus too much on.
And you can never go below n over k.
You might. Like this is the upper bound.
No, I'm saying for large k.
Yeah, because you can just think of an input graph where you are partitioned into k. Yeah, so that always is a example that you can't beat. Okay, so this is based on like something called sum of squares, which is the way to like strengthen SDPs with like some more constraints. I won't tell you much about it today. One reason I was excited at the time we wrote this paper was because it was a natural example of a problem where constant rounds of SOS actually allow us getting a great gain. There are examples of SOS, concepts of committal optimization, where there are great gains possible if you allow me super constant rounds, like usually super polynomial time. But this is an example of optimization, combinatorial optimization problem where constant rounds of SOS seem to help a lot. That was kind of exciting at the time. In particular, like for the fully random problem, there is no such gain. We can provably show that there is no gain to be had by going to higher constant rounds. Good. So, and this whole business really was on the backs of this whole line of work that began in this paper that Adam and I and Sushil Karmalkar wrote on list decodable learning. So a bunch of things happened after that, and this basically made a machine which reduced some list decoding kind of problems to some specific certification questions, which we solved for this problem. So we can just plug into the machine, and that's how this algorithm works. So I will not tell you much more about this. That's pretty much it. Okay. Today I'm going to tell you about this slightly newer result, still from last year. So sorry about that. Where we can get a super fast algorithm. I have very few talks where I can describe the exponent of polynomials explicitly. So when I could do it, I thought I should take the opportunity. So here is the exponent of the running time. Omega is the matrix multiplication constant. So it's less than cubic if you apply fast matrix multiplication. And it works if k is at least square root of n times log square n. Okay, so it basically gets down to root n up to some polylog n. And importantly, we don't know how to handle monotone deletions. In fact, that's the number one question I'll ask, because it kind of appears like there could be a gap that arises entirely because of monotone deletions now. So I don't know if that's true, but that would be very interesting. Actually, this is based on a new positive, I'll tell you why I say that, connection to certifying restricted isometry property of matrices. If you have seen that before in the context of compressive sensing, I'll tell you a little bit more about it very soon. But you might have seen it, for random matrices, like random rectangular matrices. I'll need this RIP property for correlated rectangular matrices now. But it turns out that there is a very general theorem that shows that even such correlated rectangular matrices, when they have appropriate structure, do satisfy this RIP property, and this will be crucial to the success of the algorithm. Okay, so this is the cool thing. I say positive connection because there are lots of hardness results for certifying RIP by reducing to Clique. But I'm actually going to use it positively. I'm going to actually reduce the semirandom Clique to RIP, and then I will solve the problem using it. Okay, good. And the punchline is that it's a super simple algorithm that I will describe to you on the board. I should say that the same algorithm's analysis was improved to k root of n log n very recently by Venkat Guruswamy and his student Sinpo Wang. Basically, we had a suboptimal proof of RIP-ness of the matrix that arises, and then they hacked out the right proof. The right proof gives square root of n log n here. The gap between root log n and the root n thingy in the fully random case seems real. In fact, Steinhardt conjectures that it's optimal. We don't know, but this algorithm certainly will not succeed below this. Like this is the end of the road for this kind of an algorithm. Okay, does it make sense? Good, so I'm going to tell you about this algorithm. In fact, I'm going to describe it fully now. Okay? Any questions before I do that? Okay, great. Actually, that would be great. And can we just like send this thing up, because then I can use the central board.
Sorry, in that blank space is supposed to be the minus S.
Yes, sorry about that. That's my bad animation. Come back if I...
without monotone deletions, you just mean you're not touching the boundary?
Yes. So the SDP algorithm succeeds if I touch the boundary, but I won't tell you that. Okay, I'll tell you an easier algorithm that has this downside. I'm not sure how to turn off. There is, oh, I see. Oh, okay. Oh, you did it. Oh. You can see this is the theory group. No way, huh?
It is right. Let me push a couple of random buttons.
Oh, perfect. All right. Oh no. I celebrated too quickly. I think this is fine though. We can live with this, right? Oh yeah, okay, good.
Adam, you can just turn it off. It's a power switch there.
No, there's a button that says all off. All off, actually.
Okay. So I want to start with a greedy algorithm. It won't give you the result, but it will be the starting point. Okay? So, I want to, so at the back of your mind, you should think of trying to invent a version of this greedy algorithm that just takes the biggest degree vertices. Okay? But now I won't do it on degree, I'll try to do it on common neighbors. Okay? It will kind of sort of work, but not quite, and then we'll see how to fix it. Okay? Good. So let me write down the algorithm. Guess a vertex in the planet Clique. Okay? Now, let's say the vertex is V, and let NV in plus minus 1 to the n be the neighborhood indicator vector of V. So, NV of J tells me whether V has an edge to J or not. It's plus 1 if there is an edge, it's minus 1 if there is no edge. Okay? Good, so that is the neighborhood indicator vector. So my step 1 is guess a vertex. Eventually, I'll just repeat a bunch of times, and then I'm bound to hit S star because it is like root n size, so n over k guesses would be enough, right? Once I do this, take all vertices J such that NV has a large inner product with NJ. Okay, let's think about what large means. I would like so if I guess the vertex in S stars correctly, I would like all the vertices in S star to satisfy this bound, because those are my good set. Like those are the ones I want to collect. Okay? So let's try to estimate what this inner product quantity would be if I did, look at a vertex J which is in S star.
Okay. These vectors are just like rows of the adjacency?
Yes. Yeah. Yes. Yeah, I'm writing this in a funny way because I'm going to define some versions of these vectors which are not rows of the adjacency very soon. Okay, so I'll compute here. So NV dot NJ. So let's imagine this picture in our heads. This is like S star. This is V minus S star. Now look at NV and NJ. If I look at the coordinates in S star, they all will have plus 1, plus 1, plus 1 here. Okay? So this inner product contribution from these guys would be K, the size of the clique. And now, here, NV and NJ are both random vectors because the cuts were random. So I should expect and I'm paying root log n because I'm doing union bound, etc. eventually. So this is just, okay, you agree with this? So K is much bigger than root of n log n. So, I'll say that this is at least, let's say, k over 2. Okay? So that's my threshold. Okay, that's my algorithm. So now, let's try to understand, whether I'm doing well. First of all, I'm going to guess a vertex in S star with roughly like, if I guess it n over k times, I'm bound to get a vertex in S star. Right? Like with constant probability, I can get logs n and I can make it high probability, etc. too. So the guessing part is not a big deal. So the only question is, if I do take, for a V that does belong to S star, if I take all the J's which satisfy this property, am I getting a good estimate of S star? Okay? So claim 1 is easy, which we already argued. Let's call this set S sub V. S sub V contains S star, which is what we argued with high probability, right? So the key question is, how many spurious vertices am I collecting? This is the key question. And now the issue is that really, like, I have a big worst case part in my graph, right? If I look at a vertex here, its edges to V minus S star were completely up to the adversary. They could engineer it so that, they have big enough product with, like, the adversary is trying to engineer this graph after looking at the neighborhoods of all these vertices. They could try to engineer it so that, I have great enough product with many vertices in S star. Yes? Then I'm in trouble as such. The point I'll try to argue now is that they can't really do that much. There is a non-trivial guarantee you can extract even from here. Okay? The rough intuition is that the neighborhoods here, when restricted to these set of vertices, are random. So these are like spread out vectors. An adversary, even a worst case one, cannot try to somehow correlate with so many vectors at the same time for all. Like, this is the intuition. Right? Like it's kind of going to be physically impossible, like L2 impossible to do this. Okay. So let's see why. Okay. So here's how I'm going to prove this now. Fix a vertex, let's call it U, in V minus S star. Okay. Then the number of vertices J in S star such that NU dot NV is bigger than K over 2 is at most, okay, I'll prove this to you. It's everything, from now on should be easy. So I'll prove this in a second, but let's see, what this means. Okay?
You think that'd be a bad bet? That seems low.
Yeah, you'll see. It's non-trivial. It won't give me the result I promised you, but it'll give me a non-trivial result. Okay? And this is going to be simple L2 bound. Okay? I'm not doing anything clever here. So why is this helpful? Let's see. Yeah. NU. Sorry. All good? Okay. So why is this helpful? Let's see. Okay. So I look at, I'm saying, for every vertex in V minus S star, there cannot be more than like n square over k square vertices in S star that it simultaneously correlates non-trivially with, right? So in total, so you look at all pairs, V minus S star comma S star, such that the pair is correlated. How many such pairs? Total number of correlated pairs is order of n cubed over k square, right? Because there are n vertices, or at most n vertices in V minus S star. Each one has like n square over k square highly correlated vertices in S star. So in total, n cubed over k square pairs. Okay? Therefore, a typical vertex in S star should have order of n cubed over k cubed bad U in V minus S stars. Like I'm just saying, in total the bad pairs are n cubed over k square. There are k vertices, right? How many, if I look at by Markov, half of the vertices in S star cannot have more than like twice whatever this bound is, number of bad neighbors. So you see, like if this is the average number of bad vertices for any S star. I'm saying, half of the vertices in S star should not do more than twice the average. Does that make sense? So now let's see, Adam's question, whether this is a good bound. Okay? So this analysis implies that when I run this algorithm, SV will contain all of S star, k vertices, plus it will contain about n cubed over k cubed of bad vertices. Okay? It turns out that if the fraction of bad vertices is a small constant, like let's say 1%, then there is some simple cleanup you can do to remove those 1% vertices. So let's say, as a first cut, our goal is simply to recover a set such that 99% of the set is S star. We don't want to exactly recover S star, we want to get a set which has 99% of the vertices from S star. Okay? So, to ensure that, I just need to ensure that order n cubed by k cubed be much less than k, much less than, let's say, 0.01 k. Yes? When will that happen? This happens if and only if k to the 4 is bigger than n cubed or k is bigger than n to the 3/4. Okay? This is not good in the sense that this is not matching the best form, but it's non-trivial. It wasn't clear why you should be able to do k which is n to the 1 minus epsilon, and you're saying it's super dumb, greedy algorithm already does it. Okay? Does that make sense? Okay, good. So, for my next trick, I'm going to show you how to upgrade this algorithm to actually get n to the 0.6. Okay? I'm going to do 3 tricks. Okay, so here is so how do I upgrade this algorithm? How might I do this? Well, I'm going to guess a pair of vertices in S star now. Okay? And I'm going to define n v1 v2 to also be a vector in plus minus 1 to the n with the property that n v1 v2 at j is the product of plus minus 1 indicators of j v1 being an edge and j v2 being an edge. In other words, at j, I have the parity of the number of edges between v1, v2 and v2. Okay? Definition is clear? Okay, very good. And now, my algorithm is to simply take the vertices which are non-trivially correlated with n v1, v2. The analysis for the good vertices is exactly the same. Because if I look at 2 vertices in S star, how does their behavior on S star look like? They are still plus 1s. Okay, product of plus 1s remains plus 1s, no change on the clique. So, I'm going to collect all the vertices in the clique. This behavior looks the same, okay, because, there is still like independence, etc., remaining in every row. So like the union bound still works out. You could complain, you say, okay, your union bound is on n square thing instead of n now, whatever. Yeah, there is a 2 here and my O captures it. Okay, but there is no real change, okay? Good. So this part works out fine. Claim 1 basically goes as is. What about claim 2? Am I making an improvement there or not? Okay? So to see whether I'm making an improvement, I want to give you a proof of claim 2 first from the previous thing. And then, I'll come back and modify it to also give you the proof of, this improved claim 2. Okay, so, see. So first, let's prove the previous claim 2, okay? There are various ways to prove this, but I will prove it in a way that is notationally similar to what I'm going to do next, okay? So let's look at the following matrix. Let's call it H. It's going to be n by k matrix. And in this matrix, I'm simply populating the neighborhood indicator vectors, okay? The columns are neighborhood indicator vectors of the k vertices in S star.
Okay. The new product ones or the old ones?
No, this is the old one right now. It will become n by k square once I do the product ones. Okay, but let's do the old one now because it's going to be a simple L2 proof. Okay, good. So this is like, n v1, n vk, and v1, v2, vk are in S star. Okay, so now let's look at, so take any vector u. Okay, and look at what u transpose h. Now, let's say u is a vector that correlates well with some subset t in S star. Okay, so let t in S star be such that nu nj is larger than k over 2 for all j in t. These are the bad vertices. Like, from the perspective of u, they're the good vertices. Okay? So what does u transpose h1t look like? This is the 0, 1 indicator of vertices in t. Well, what am I really doing? U transpose h basically takes the inner product of the vector u with nv1, nv2, etc. And then I'm summing up the contributions from columns corresponding to vertices in t. Well, this must be, just by our assumption, k over 2 times t. Yes?
No, why is that?
Because, u is a vector which is correlated with nj, like u is a vector that's correlated with nj up to k over 2, right?
Oh, and then t.
And yeah, t is the subset of S star that, it's correlated with. So I'm saying if I take this bilinear form, I'm literally adding the correlations from the columns that are correlated with at least, with u to at least k over 2 level. So I get that lower bound. On the other hand, I can give a spectral upper bound on this matrix. This is an n by k random matrix. Okay? We know its largest singular value. It is square root of n plus square root of k. Okay? So I know that this is at most u, because k is always tinier than n, this is, at most root n times. Okay, so let's see what happens. This is square root of size of t. This is, this is square root of n because u is a neighborhood, like, it's plus minus 1 man. Okay, you still good with this? So what does it resolve to? So size of t is at most square root of n over, wait, did I do it right?
There are two square root n.
Where is another square root? Oh, sorry, yes, very good. Otherwise I get too good about it. Okay, so now I'm done. Square it and you get n square over k square. You're all good with this? Yes? Okay. By the way, this is a simple L2 argument, so you can do many different ways, but I like this because I'm going to just do some minor changes now. Okay? Good. Alright, so that's the argument, for the previous version. But now, I'm going to prove a similar claim via a similar trick, but now I have an n by k square matrix. Okay, so let's draw because the drawing is important. So I'll also erase this. Okay, it's easy, you can replicate it easily. Now the drawing would look, remember k is at least root n log n, so k square is bigger than n. So the drawing will reflect this, okay, and this is important. You should imagine, the shape of the matrix has changed. Right? It was tall, thin, but now it is whatever is the opposite of that. Okay. Okay, good. So that's the matrix. That's how it looks. I'm going to do the same argument. What happens if I run the same argument? I claim that you are in trouble. Why? The key point is that the spectral law of this matrix is governed by the larger dimension. In the previous argument, n was the larger dimension, so we got root n. But now, if you do it, trivially, you do the L2 argument, you get square root k square. If you run this argument, you get nothing. okay, because the shape of the matrix has changed, okay. Here is how we will exploit the further, like, additional property of a problem so that we don't have to pay in the spectrum now. The key point is that I'm always gonna take this 1t, the indicator of columns that I was using, I'm always gonna keep it to be a sparse vector. So the idea is that I will pay in the sparse operator norm of this matrix and not the operator norm. Okay? So let's try to make it all formal. So if I run the same argument again, let's see what happens. Okay? So I have U transpose H 1 sub T. Okay? But T is this time a collection of pairs. It's a set of columns that correlate well with this vector U. Okay? I'll still get K over 2 times T as a lower bound here. That's still the same. Okay? I just want to improve the upper bound. Okay? What's the upper bound I should use? Well, let's say T is R sparse for some parameter R. Okay? Then I pay in the sparse operator norm. Let's call it R operator.
Sorry, does R sparse mean all the columns are R sparse?
No. I'm just saying, so let's make a definition here. Definition, the R sparse operator norm of H is simply max over all vectors V. V is R, has at most n non-zeros, is unit norm, H V.
Yeah, but this is hard to compute.
Yeah, I'm now going to compute it. I mean, the computation is clear. This is the computation I'm doing. This is only in the analysis. Yes. Okay, but this upper bound is valid, right? I don't know what this quantity is, but the upper bound is valid. Okay? So now, let's understand what can we prove about this. We are hoping for a bound on HR2 which is much better than the operator norm, right? That's our hope. Yes?
So what is R here?
Good. What R am I going to choose? Okay. Yeah, no, it's a great question. Let's think about this. So H has n rows and k square columns. And it's like, wide and fat matrix. Is that how you describe this? Okay. Okay, very good. So if I look at this, say this was a random matrix. It isn't. Say it was a random matrix. Then you hope for an RIP property to hold, in the sense that you expect that this matrix will behave like an isometry on vectors of what sparsity? Well, you might remember it in the opposite direction. If I have to do k-sparse vectors, then I need k log n columns. In my world, you can think of it as R should be n over log n. Like, if R was at most n over log n, then I should be able to hopefully argue some restricted isometry property of H and get a bound in terms of this sparse operator norm. Okay, so let's do some heuristic calculation and then we'll basically know what parameter we're looking at. So to answer your question, Shuchi, what R am I going to look at? I can look at R anything ranging up to n over log n or n over polylog n. Okay, now if T is bigger, what would I do? Doesn't matter. Take like any subset of n over log n elements out of it, use that in the argument. I don't have to take T to be the set of all things that are hypothetically large. Just choose a subset which is like, n over log n large. I'll do this whole argument for that subset. Okay, make sense? Okay. So let's at least guess what we expect this quantity to look like. Okay. So now I'm going to rely on some analysis, some vague understanding of RIPness that you might have seen before. So if H is n by k square, like in our case, then I claim that 1 over root n H should behave like an isometry on n over log n sparse vectors, in the sense that this guy should have operator norm order 1. Isometry means that it actually is 1 plus delta, but I really don't care about that. I just care about constant. Okay? Does this look all right? Like 1 over root n should be obvious in the sense that, I'm just scaling so that each row contributes the same L2 mass, and like together they contribute 1. Okay, does it make sense? You can think of it this way. Each row is like if it's a random vector, each row is basically going to get you something that looks like the L2 norm, because that's how, G dot V works if G is a Gaussian. And then I have n rows. So if I do 1 over root n scaling, I should basically have the L2 norm preserved. Does that make sense? Okay, so this is all I need from you. Okay, assume that this is true. Okay, and let's see what happens in our argument. Okay, so so we are assuming implicitly that R is at most n over polylog n here. Okay, I will use for HR2. Actually, let's maybe plug it in this way so that computation is a bit easier. Then I get, order 1 here. Agree? Okay, so let's, resolve this and see what happens. Well, this is, root n still. This is root t still, which is root r for us in this new notation. So we have order root nr right hand side. And then, we have at least k times r. Okay, so what do I get? So I get root r is at most I feel like I've made the same error somewhere again. Oh, sorry, I had a 1 over root n now. Okay, good. So r is at most again n square over k square. The point is that I got the same bound. This is the punchline, right? Like, by resorting to the R sparse operator norm, I got the exact same bound, even though, the spectral norm estimate would never have gotten me this bound, right? We already saw that to get this bound, I need to have root n spectral norm, but the spectral norm is larger. It is root k squared, even if it's a fully random matrix. So we got an estimate which is the same as before, meaning we kind of sort of paid only root n in the estimate. Does it make sense? Okay, so, okay, very good. So I'll finish in like 2 minutes, okay? Okay, so what I'm going to do in the next 2 minutes is first of all tell you what this bound buys you, okay, the new bound. And then, I will, in 1 minute, sketch for you why this is RIP. Okay, that I'm not going to prove it because it requires chaining and all. So that part is going to be black box. But I'll just argue to you why this estimate is actually useful. Okay, very good. So let's erase this part.
Question.
Yes?
It looks like you just played with norms somehow, it just popped out. Is there some intuition?
Is there some intuition? I think, it's somehow the way I thought about this, the way we guessed that this could be true is because we thought this matrix has dependencies, but we thought for the purpose of how many vectors can you somehow correlate with, it should behave, really like a random matrix. You see what I'm saying?
Why the product?
Huh?
Why the product?
Oh, why the product? It's not, okay, so if I want to have RIPness here, for example, I would want at least the individual entries to be mean 0. The product is not even mean 0.
Right.
Like, sorry, I mean, like, if you take any other version, it won't even be mean 0. Like, think, how would you create an unbiased random variable out of like 2 plus minus 1 random variables? Seems like XOR is the right way.
The product of any one and
That's all I'm using, by the way, here. Take any operation that would.
Using the fact that that's mean 0.
Yeah, that's it. Nothing better than
you
that.
haven't proved the norm bound, which you won't do.
Which I won't do. I guess I'll tell you why it's true. Okay, I will demystify it too. But first I want to show you that this estimate is useful. I got the same estimate, so why are we succeeding now? Well, the key point is, let's do the same calculation from, previous thing again. How many pairs are bad? Okay. Well, for each u, we are saying there are n square over k square things that are bad. But this time it's out of k square, not k. This is the win. Okay. So the total number of bad pairs is at most n cubed over k square still, because there are n possible values of u each one has n square over k square bad vertices in S star. So the average number of bad j in V minus S star for a typical u in S star is at most n cube over k to the 4 because there were k square pairs. Okay, now I am you can see I'm winning because I just look at typical things, I pay some constant over here and I'm comparing this against k. So I win if n cubed over k to the 4 is much less than k, or k to the 5th is bigger than n cubed, or k is at least n to the 0.6, which by the way we are beating n to the 2/3. So no need of SDPs, no entropy, whatever. This like trivial greedy algorithm already beats the previous thing. Yeah, excellent, you can, and that gets you into the 1/2 plus epsilon, so it replicates the result with SDPs. Okay, so you can ask, how do I prove the actual result I claim? I'm not even going to show you, but take triples, that's it.
So 1 over epsilon tuples give you the...
1 over epsilon pairs already give me, like, okay, so there are two ways you can repeat this algorithm. One thing I can do is like construct n v1, v2, v3. It's like take triples and take their parities. That one gives me the answer. That one gives me root n log square n. But there is a different way, intermediate, you can like, amuse yourself by doing the n v1, v2, but repeating this algorithm 1 over epsilon times. Yeah, because you say, okay, guess multiple pairs and like, take if you're correlated with every one of the guessed pairs. That one gets you into the 1/2 plus epsilon. Triple thing gets you root n, and you might guess what happens to 4 tuples. Any guesses? Nothing. Nothing happens. That's it. Okay, so it gets you, like it doesn't hurt you, but it also doesn't help you. Okay, so to end, let me just tell you why this matrix is RIP. Why should you expect it to be RIP? Because this is an amazing result, I think. It's due to Rudolph's version in. It's really powerful. Like so they wrote it down for frames and all. It's a bit hard to interpret, but I'll write it in the language I wrote here so that it's become obvious. So here is a result of Rudolph's inversion in. This is actually pretty old result. So here's what they proved. Let D be any distribution on R capital N such that its mean is 0 and covariance is identity. So it's isotropic. Okay? Only one more condition. L infinity norm at most order 1. Every vector in the support is, L infinity bounded. Okay, then if I construct a random matrix, if I sample V1, V2, Vr independently from D, and I take the matrix that populates these as rows, then this matrix is optimal RIP. Okay, what's the key point? D need not be a product distribution. The entries of vectors in D can be arbitrarily correlated. Okay, like 3-wise correlations could be non-zero, 4-wise correlations could be non-zero, as long as their pair-wise correlations, are 0 unless they are equal. That's enough for this result. It only needs observations about first two moments and L infinity norm. Okay, take any distribution, take independent rows, make a matrix out of it. That's going to be RIP. Okay, this log square R is what we lost to get log square, but our situation is even more structured. We are only looking at 0, 1 vectors. So Venkat and Sinpo basically observed that you can do a slightly more specific version of this argument that only works for 0, 1 vectors and only works for the upper bound direction and get root n log n. That's it.
What kind of concentrations do you use?
Oh, this is chaining. This is not state. This is not off the shelf.
I want like the optimal bound. I don't want to do the chaining.
I don't know how to prove anything better than root R if you want to use off the shelf. This is a powerful tool. Yeah, in fact, this is where we were stuck. So for a while, we were stuck on like how to prove this, and we had more complicated arguments using, directly analyzing the spectrum of this matrix. But yeah, this it's a super powerful. Like if you heard of like this frame sampling and orthonormal frame sampling, that's where like this thing comes out. It doesn't matter if you haven't. Yeah. So like for example, the early attempts to prove the subsampled Fourier matrices RIP, they were like this is the context that they were proving this in, because look at the Hadamard matrix. Right, like it's a deterministic matrix, but if I sample rows and columns out of it, it will be isotropic. Okay, so this, for example, can be used to show that subsampled Hadamard matrices are RIP, a fixed matrix. So this is the context that they were proving it in. Anyway, that's all. Yeah, sorry, I went a little bit over.
No problem.
Just one open question to end with. This algorithm very strongly utilized that the edges that went out of S star were chosen at random. If I do deletions, this RIPness breaks. So I don't know how to do this simple algorithm if there is a monotone adversary. For that, the best thing I know is still the SDP I showed you, like SDP based result I showed you. It would be really great if there was a way to adapt this with some more tricks to make monotone deletions work. That's it.
Quick question? Or?
If you switch the orders a little bit, so the adversary first picks the P minus S star, and then you do random edges, and then you allow deletion.
Then it's easy.
Then, oh, I see. So that's a solved model?
As in, like, it's I think in some sense, you're forcing the adversary to be oblivious.
Right.
And the point is that to defeat even, like, this algorithm will work simply there. Right, like, because and you don't need any analysis in some sense. Like, you see, like in some sense, the adversary to fool you has to really know your vectors and try to like code. That won't happen naturally. So if you're oblivious, it's easy. So really, like the power in this model comes from adaptive adversaries, like adversaries that get to look at the sample graph and then make their choices. Yes.
Are there any other interesting distributions for the boundary edges that would allow addition?
Oh, yeah. Great question. Yeah, in some sense, the SDP based bound makes it much more clear. To be honest, like, I don't think the n to the half plus epsilon bound is so bad. So, if you don't want to match root n polylog, you can work with that. And then that algorithm and its analysis is much more transparent in terms of what it needs about the edges. I can tell you what the property it needs. So look at like, this S star by V minus S star matrix, like this graph. This is the bipartite graph, and it's a bipartite random graph before deletions. Okay, so let's look at the graph before deletions. It turns out that what governs your ability to spot the planted clique, like learn it or whatever, find it using algorithm, is what is the bound on unbalanced bicliques that you can certify in this graph. So by unbalanced bicliques, I mean cliques that use about log n vertices on the left and about root n vertices on the right. Okay, so for whatever distribution, you can certify not just the truth, but you should be able to like efficiently certify, find a sort certificate of that there is no log n by root n biclique in this random graph. You will also be able to handle deletions, etc. So for random graph, it is true. There are more distributions, like for example, bounded wise, like log n wise independence would be enough, right? I don't know other interesting choices, but at least it's an explicit criterion for where the algorithm will work.
Gotcha. Do you have a question?
Yeah, okay. For like including deletions, do you expect the same algorithm to work and the problems in the analysis, or?
The same algorithm will certainly not work because the RIP is simply false. You will have to modify it somehow, but I still, yeah, okay, let me say, I don't know is the best answer. There could be a modification of this greedy algorithm that could work. I don't know, I've tried and I've failed. There could be an SDP that somehow does this and therefore also does that, and then everything would be great. But in that also I've failed. Like, when we wrote the paper, we upselled it at, well, this is an algorithm that's super simple, does not even use the SDP. But the real truth is that I don't know how to use the SDP. Like I would be happy if there was an algorithm that used an SDP and got the same result, because then it would likely also work with deletions. SDPs are naturally robust. So the feature is the bug. Like, if there was a worse algorithm for this problem that got the same guarantee, it would be great.
Okay, let's thank Pravesh again.